Right now, about 600 light-years from the bed you're lying in, it is raining iron. Not rust locked away in the ground, but iron hanging in the sky as vapour, gathering into droplets on the cold side of a world and falling as molten metal through the dark. And that is one of the gentler places we're going to visit tonight. We tend to look up at a quiet night sky and read it as calm, finished, safe. But that calm over your head is a rare exception, not the rule. Out there, worlds storm glass sideways at 7 times the speed of sound. A single nebula sits colder than the universe itself is supposed to be able to get, and a star 40 times heavier than our sun is being eaten alive, thread by thread, at this very moment. Tonight we're going to count down the 10 most terrifying places in the entire universe, climbing from the merely deadly to the genuinely unthinkable. And I will tell you now, before we begin, that the single most terrifying place on this whole list is not the hottest and not the coldest and not the most violent. It is a place where the very idea of a place stops working. I am going to make you wait for it. By the end of tonight you will know exactly what it is. Get comfortable. If you enjoy having the ground quietly pulled out from under your sense of what is normal, a quick like and subscribe genuinely helps this channel reach more curious minds like you. Because by the end of this, the calm sky over your bed is going to feel less like an empty backdrop and more like the rarest kind of shelter there is. Now, let's gently drift into this. 636 light-years from where you're lying right now, there is a world where the weather forecast is a sheet of falling metal. Not metal in the way we mean it on Earth, locked away in the ground as ore, waiting for a furnace. On this world the iron is in the sky. It hangs in the air as vapour, it drifts on the wind, and on the cool side of the planet it gathers into droplets and falls, the way rain falls here after a warm afternoon. If you could stand beneath that sky, and if you could somehow survive long enough to look up, you would watch liquid iron coming down out of the clouds. That is the mildest place we're going to visit tonight. I want you to hold on to that, because we have 9 more stops after this one, and each of them makes the last look gentle. The name itself tells a small story. WASP stands for a survey that hunts for planets by watching stars carefully for the tiny regular dimming that happens when a world passes in front of them. Each time WASP 76b crosses the face of its star, it blocks a sliver of the light, and from the rhythm and depth of those dips, astronomers can work out the planet's size and orbit. It is a humble way to find a monster, watching for a faint repeating flicker in a distant point of light. And yet from that flicker, and from the fingerprints hidden in the starlight, an entire hellish world has been reconstructed, a world we will never visit and never photograph, known to us only through the patient reading of a shadow. The planet is called WASP 76b, and it belongs to a family of worlds that astronomers have started calling ultra-hot Jupiters. It is a gas giant, larger than the planet Jupiter in our own solar system, and it orbits a star a little bigger and brighter than our Sun. What makes it monstrous is not its size, it is how close it sits to its star. WASP 76b circles its Sun at a distance of about 3 million miles. To put that number in a frame you can feel, the planet Mercury, the closest world to our own Sun, orbits at around 36 million miles, and Mercury is already a scorched, cratered, sun-baked rock with no atmosphere left to speak of. WASP 76b sits roughly 10 times closer to its star than that. It has fallen so far down toward the fire that a single year there, one complete trip around the star, takes less than 2 of our days. It races around its sun once every 43 hours or so, held on a leash of gravity, roasting. When a planet orbits that close, something happens to the way it turns. The same gravity that holds it in orbit also grips the planet itself and slows its spin, until eventually the world stops turning relative to its star. One face is locked toward the fire forever. The other face is locked away into permanent night. We call this being tidally locked, and our own moon is a gentle example of it, which is why we only ever see one side of the moon from Earth. But the moon is a cold, quiet demonstration of the idea. WASP 76b is the violent version. On the day side, the side that never looks away from the star, the temperature climbs past 2,400 degrees Celsius. That is over 4,300 degrees Fahrenheit. It is hotter than the melting point of iron, hotter than the melting point of most of the metals we consider sturdy and permanent. On that side of the planet, iron does not stay solid, and it does not even stay liquid. It boils. It turns to vapour and rises into the atmosphere as a metal gas. Picture the geometry of this world for a moment, because it shapes everything about its weather. With one hemisphere locked in eternal day and the other in eternal night, the planet is divided by a permanent boundary, a ring around the world where blazing daylight meets endless dark. Along that boundary, the temperature difference is savage, and savage differences in temperature are what drive winds. So a relentless gale roars from the searing dayside toward the cooler night, always in the same direction, never pausing, never reversing, a wind that has been blowing along the same line for as long as the planet has existed. It is on that boundary, the evening edge where the hot wind carries its cargo of vaporized metal into the cold, that the iron begins its long fall out of the sky. This is the detail I find hard to let go of. We think of iron as the very definition of solidity. We build our bridges out of it, our ships, the frames of the buildings we sleep in. When we want to say that something is dependable and unbreakable, we reach for the language of iron. And on the day side of WASP 76b, that same iron behaves like steam over a kettle. The atmosphere is thick with it, a haze of vaporized metal, glowing in the light of a star that never sets. Now here is where the story turns from strange to genuinely eerie, and here is where careful measurement did something that no imagination alone could have done. In March of the year 2020, a team of astronomers led by David Ehrenreich published their findings in the journal Nature. They had been studying WASP 76b using an instrument called Espresso, mounted on the Very Large Telescope in the mountains of northern Chile. Espresso is a spectrograph, which means it splits the light coming from a distant object into its component colours, the way a prism spreads sunlight into a rainbow, and in that spread of colours, hidden in the exact wavelengths that iron absorbs and emits, the astronomers could actually track the iron as it moved through the planet's atmosphere. They were not guessing. They were watching metal weather from 600 light-years away. What they saw was a pattern that only makes sense one way. On a tidally locked world like this, fierce winds blow from the blistering day side toward the cooler night side, carrying the hot atmosphere around the planet. The astronomers detected iron vapour streaming across the boundary where day turns to evening, the line they call the evening terminator riding the wind toward the dark. But when they looked at the opposite boundary, the line where the night turns back toward morning, the iron was gone. It did not come back around. Something had removed it from the air in between. The only explanation that fits is that on the night side, where the temperature drops to around 1500 degrees Celsius, the iron vapour cools just enough to condense. It gathers into droplets, and it falls. The iron rains out of the sky on the dark side of the world, which is why it never completes the journey back to morning. Let me put you there for a moment, because this is a place worth standing in with your mind before we move on. Imagine you are floating on the night side of WASP 76b, in the permanent dark, though it is never truly cold here, only less unbearably hot. Above you the sky is not black. It glows a dull, sullen red, lit from below the horizon by a star you cannot directly see, its light bleeding around the curve of the planet. The wind is screaming, carrying heat and metal off the day side at speeds that would flatten anything we have ever built. And out of that glowing haze, catching the red light as they fall, come the drops. Iron rain, each one a tiny bead of molten metal, cooling as it descends, pattering down into an atmosphere so hot that the very idea of a surface loses meaning. There is no ground to land on here in any way you would recognize. There is only the deepening, thickening gas of a gas giant, and the endless fall of metal through it. I called this the mild one, and I meant it, but I want to be honest about why. WASP 76b is terrifying in a way that is almost comforting, because it is terrifying on human terms. We understand rain, we understand heat, we understand metal. This world takes ordinary words from our own weather report, rain and wind and cloud, and fills them with iron and fire, and the horror of it is a horror we can picture. You can imagine the drops, you can imagine the glow. It is a nightmare, but it is a nightmare shaped like something familiar, which makes it the perfect doorway into everything that comes after. Because the further we go tonight, the further we are going to move away from anything the human body was built to picture, until we arrive, at the very end, at a place that is terrifying precisely because you cannot imagine standing in it at all. There is one more thing worth sitting with before we leave this world behind. WASP-76b is not rare. It is not some freak accident that the universe produced once and never again. Astronomers have now found many of these ultra-hot Jupiters, gas giants that have spiraled in close to their stars and been turned into furnaces, and WASP-76b is simply one of the clearest examples, the one where we managed to actually watch the metal fall. Every one of those worlds is out there right now, tonight, raining iron or worse under stars scattered across our galaxy. The calm, ordinary sky you grew up under, where rain means water and the ground stays solid beneath you, is not the standard model for how a planet behaves. It is a rare and gentle exception. Hold that thought too, because we are going to come back to it at the very end, after we have seen how strange the rest of the neighbourhood really is. There is a final, almost delicate horror hiding in how we learned all of this, and it is worth pausing on, because it tells you how thin the line is between a distant point of light and a place with weather. We never saw the iron rain. No camera photographed a single drop. What the astronomers did instead was watch the star behind the planet and read the fingerprints written into its light. Every element, when it is heated into a gas, absorbs light at a precise set of colours, its own private barcode. As WASP-76b passed in front of its star, a little of the starlight filtered through the planet's atmosphere on its way to us, and the iron in that atmosphere stamped its barcode onto the light. By measuring exactly which colours were dimmed, and how those dimmed colours shifted as the winds carried the iron from the hot side to the cold, the astronomers reconstructed an entire weather system from 636 light-years away, without ever seeing anything but a faint change in the colour of a distant star. Sit with what that means for a moment. A planet you cannot see, a rain you cannot photograph, a wind you could never feel, and yet we know the metal is falling, because the light told us so. This is how nearly everything on tonight's list is known. These places do not announce themselves. They hide inside the tiny details of starlight, and we tease them out one measurement at a time. The sky looks empty and finished to the naked eye precisely because all of this is written in a language your eyes cannot read. The iron rain was there long before we found it, falling in the dark, waiting inside the colour of a star for someone to look closely enough. And WASP-76b, remember, is only number 10. It is where the weather turns to metal. But metal, at least, is opaque and heavy and easy to fear. What if a world could look calm and blue and almost like home, and still be trying to kill you in a way you would never see coming? That is exactly where we're going next. 64.5 light-years away, in the direction of a small constellation called Vulpecula, the little fox, there is a planet that would stop you in your tracks if you saw it hanging in space. It is blue. Not a pale, washed-out blue, but a deep, rich cobalt, the colour of a calm ocean seen from high above, the colour we have spent our whole lives learning to read as safe. If you were an explorer drifting through the galaxy, tired and looking for somewhere that felt like home, this is the world that would make your heart lift. It is called HD 1897333b, and it is one of the most thoroughly studied planets outside our solar system, because it happens to be relatively close, and it crosses in front of a bright star, which gives astronomers a clean, repeated look at it. And everything that look has revealed tells the same story. The most welcoming colour in the sky is a trap. Let me start with how we even know its colour, because that fact alone is quietly astonishing. In the year 2013, astronomers using the Hubble Space Telescope measured the actual visible colour of HD 1897333b. This had never been done before for any planet beyond our own solar system. Think about what that means. These worlds are so far away, and so lost in the glare of their stars, that for most of them we can only infer that they exist at all by the tiny dimming they cause when they pass in front of their sun. But for this one, the astronomers watched the total light of the system just before the planet slipped behind its star and just after it emerged. By measuring how the colour of the combined light changed when the planet's own light was subtracted, they pinned down the planet's true hue. It came out a rich azure blue. For the first time in history, we knew the colour of another world, and the colour was the colour of home. This is worth pausing on, because it is the exact trap the planet sets. Our brains are wired, by millions of years of life on a water world, to read that particular blue as a promise of safety, of moisture, of somewhere the body could survive. It is the colour of the thing we most need. And HD 1897333b wears that colour like a lure, produced not by anything gentle, but by a haze of glass-forming particles roasting in a furnace of an atmosphere. The signal our instincts trust most is precisely the signal this world uses to disguise the most hostile conditions imaginable. It is camouflage, though the planet is not hiding on purpose. The universe simply happened to make its deadliest disguise out of the one color we were built to love. But the blue of Earth and the blue of HD 189733b come from opposite sources, and that difference is the whole story. Our planet is blue because of water, because of oceans catching the sky, because of the way our atmosphere scatters sunlight. HD 189733b has no oceans. It is a gas giant, roughly the size of Jupiter, and it orbits its star so closely that it is savagely hot, with temperatures running somewhere between about 900 and 1,200 degrees Celsius. Nothing about it is calm. Its blue comes from something else entirely. High in its scorching atmosphere float countless tiny particles of silicate. Silicate is the raw material of glass. It is what we melt in furnaces to make windows and bottles. On HD 189733b, these particles of glass stuff hang suspended in the air, and they scatter blue light more strongly than other colours, throwing that rich cobalt shade back out into space. The planet is blue for the same reason a hazy sky can glow, except the haze is made of the ingredients of glass, superheated, drifting through an atmosphere hot enough to make them. Before we assemble the full picture, hold the wind speed against something you know. The fastest passenger jets cruise at a little under 600 miles per hour, and the fastest sounds that can travel through our own air move at roughly 760. The winds on this planet blow at around 5,400 miles per hour, which means the air itself is moving faster than sound can travel through it, many times over. On Earth, when an aircraft merely reaches the speed of sound, it cracks the sky with a sonic boom that rattles windows on the ground. On HD 189733b, the entire atmosphere is permanently everywhere, moving at many times that speed, a continuous planet-wide scream of air that would never, for a single second, fall quiet. Now put the pieces together, and you arrive at one of the most quietly horrifying weather systems anyone has ever described. This planet does not just contain the raw material of glass, it has weather, and the wind on HD 189733b is not like any wind on Earth. Astronomers estimate that it blows at speeds around 5,400 miles per hour. Let that number settle. The fastest sustained winds ever recorded on Earth, in the heart of the most violent storms, top out at a few hundred miles per hour, and they flatten cities. 5,400 miles per hour is roughly 7 times the speed of sound. It is wind moving so fast that the word wind almost stops applying, and into that wind the silicate particles are thought to condense, gathering into something like grains or shards of glass. Which means that on HD 189733b, glass does not fall gently from the sky the way our rain does. It is driven sideways, horizontally, as a scouring, screaming blizzard of molten and hardening glass, travelling at 7 times the speed of sound. Stand in that for a moment, in your imagination, from a safe distance where nothing can reach you. You approach a blue world, the friendliest sight you have seen in the long dark between the stars. As you get closer, the ocean blue resolves into a churning, glowing atmosphere. You feel, if you could feel anything, the first touch of the wind, and it is not a breeze, it is a wall, and carried in that wall, catching the light, is a horizontal storm of glass, flying fast enough to erase anything it touched. The planet that looked like a place to rest is a sandblaster the size of Jupiter, and its sand is glass, and its wind could cross a continent in the time it takes you to read this sentence. The most beautiful thing in the sky is the thing that would take you apart the fastest. I keep returning to that inversion because I think it is the real lesson of this second stop, and it is a lesson the rest of tonight is going to keep teaching in harder and harder forms. Out here, appearances are the first thing that betrays you. On Earth, our instincts are mostly reliable. Blue water is usually safe to drink or swim in. A calm colour usually means a calm place. We evolved on a world gentle enough that our senses could be trusted most of the time to tell us where the danger was. But those instincts were calibrated for one small, unusually kind planet. Carry them out into the wider universe and they will get you killed because the universe did not agree to keep our colour code. Here, the softest, most inviting blue in the heavens is a blowtorch wrapped in the appearance of an ocean. There is a further point hiding in HD 189733b. and it is worth naming before we move on. This planet is close in cosmic terms. 64 light-years is nothing against the scale of the galaxy, which stretches 100,000 light-years across. HD 89733b is practically a neighbour, and it is one of the best-studied worlds we have ever found, precisely because it is so accessible to our telescopes. It is not some distant curiosity seen once at the edge of what we can detect. It is a world we have looked at again and again, measured carefully, come to know. And the better we have come to know it, the worse it has revealed itself to be. This is a recurring pattern in the exploration of other worlds. The more closely we examine a place, the more we tend to find that the universe's imagination for hostility runs far ahead of our own. We keep arriving with our gentle earthly expectations, and the cosmos keeps quietly setting them on fire. It is worth knowing that HD 89733b is not just a horror story. It is one of the most valuable planets in all of astronomy, a kind of testing ground where we first learn to read the atmospheres of distant worlds at all. Because it is close, and it crosses a bright star, it became the planet where astronomers practiced the techniques that now let us study atmospheres across the galaxy. On this world they detected water vapour woven into that murderous air. They mapped its temperatures, finding the searing day side and the merely brutal night side. They even watched its atmosphere being slowly stripped away and boiled off into space by the fury of its nearby star, bleeding into the dark like steam off a kettle. Nearly everything we know about how to characterize an alien sky we learned in part by staring at this beautiful, lethal blue world. And that is its own small lesson. The planet that would kill you the fastest is also one of the most generous teachers we have ever found, because its closeness and its brightness let us see it clearly. There is a pattern in that worth carrying forward. The universe's most hostile places are frequently its most instructive ones, precisely because their extremity makes them easier to study. A gentle, ordinary world gives up its secrets slowly. A world that storms glass at 7 times the speed of sound wears its physics on the outside, blazing and obvious, for anyone patient enough to look. We learn the most from the places that would harm us the most, which may be the strangest bargain in all of science. So we have a world where it rains iron, and a world where it storms glass sideways at 7 times the speed of sound. Both of them are planets, at least, worlds with a shape and a sky, places you could in principle orbit and study and name. Both of them are hot, and heat is a danger we understand in our bones, because we have all flinched away from a flame. But the next place we're going flips that instinct completely on its head. It is not hot. It is the coldest place anyone has ever found anywhere in the entire universe, colder, in fact, than the universe itself is supposed to be able to get. And to understand why that is even possible, we're going to have to look at what the temperature of empty space really means. About 5,000 light-years from here, in the southern constellation of Centaurus, there is a faint and beautiful shape in the sky that looks a little like a bow tie, or the wings of a moth, 2 soft lobes of glowing gas spreading out from a dying star. It is called the Boomerang Nebula, and from a distance it seems gentle, even lovely, the kind of ghostly structure that fills the picture books of astronomy. But this is the coldest place anyone has ever found in the entire universe. And I do not mean it is one of the cold places. I mean that as far as we have ever measured, in all the sky, in every direction we have pointed our instruments, nothing else comes close. To understand why that is genuinely frightening, and not just a piece of trivia, we have to talk for a moment about what cold actually is, and about the strange fact that the universe has a temperature all its own. Let me start with the bottom of the scale. There is a coldest possible temperature, a hard floor below which nothing can go. We call it absolute zero, and it sits at about minus 273 degrees Celsius, or minus 460 degrees Fahrenheit. Temperature, at its heart, is just motion. It is the jiggling and trembling of atoms and molecules. When something is hot, its particles are moving fast, crashing and vibrating. When something cools, that motion slows down. Absolute zero is the point where the motion has slowed as far as the laws of physics will allow, where there is essentially no thermal energy left to take away. You cannot get colder than that, because there is no colder than that. It is the true bottom of the well. Now here is the part that surprises most people. Empty space is not at absolute zero. You might think that the great darkness between the stars, far from any sun, would be as cold as it is possible to be. But it is not. Everywhere in the universe, in every direction, there is a faint background of warmth left over from the birth of everything. When the universe was young, less than 400,000 years old, it was a searing hot fog of particles and light. As the universe expanded over the following billions of years, that light stretched and cooled, but it never went away. It is still here, filling all of space, a whisper of heat from the beginning of time. We call it the cosmic microwave background, and it has a temperature of about 2.7 degrees above absolute zero. That number is the natural temperature of the universe. It is the warmth of empty space itself. Drift out into the darkest, emptiest void you can find, far from any star, and you will still be bathed in that 2.7 degrees. It is the coldest that ordinary nothing gets, and the Boomerang Nebula is colder than that. Its temperature has been measured at about 1 degree above absolute zero. 1 single degree. That is colder than the cosmic microwave background. It is colder than empty space. It is colder than the leftover heat of the Big Bang, the warmth that soaks through every cubic inch of the cosmos. Somehow, in this one place, a natural object has managed to fall below the temperature of the universe it lives inside. It is like finding a spot in a heated room that is colder than the air being pumped into it. It should not happen on its own. Something has to be actively pulling the heat out faster than the universe can put it back. Something in the Boomerang Nebula is running a refrigerator, and no one built it. It is hard to overstate how counterintuitive this result was when it arrived. Astronomers expect the coldest places to be the emptiest and most isolated ones, drifting far from any source of heat. But the boomerang is not simply sitting passively in the dark growing cold. It is doing something actively that no still and empty patch of space could ever do. It is driving its own temperature down below the universal background, which is a little like discovering a pond that is frozen harder than the freezer it sits inside. The only way that happens is if something is pumping heat out faster than the surroundings can pour it back in, and in the boomerang that something is the sheer, relentless speed of a dying star's outflow. This was discovered in the year 1995 by two astronomers named Raghvendra Sahai and Lars Åke Niemann, using a telescope in Chile tuned to the faint radio glow of cold gas. When their measurements came back showing a temperature of about 1 degree above absolute zero, it made the boomerang the coldest known place in the cosmos, a title it still holds. And once they understood what was happening, the mechanism turned out to be a piece of physics you have felt with your own hands, scaled up to the size of a dying solar system. You have felt the principle behind the boomerang's cold with your own skin, even if you never named it. When you press the valve on a can of compressed air and the can turns frosty in your hand, that chill is the same physics. When the air rushing out of a bicycle tire feels cool against your fingers, that is it again. A gas that is allowed to expand into more space spreads its energy thinner, and its temperature drops. It is one of the most reliable rules in all of physics, and it works on every scale, from the nozzle of a spray can to the death shroud of a star. The Boomerang Nebula is simply that same familiar chill, scaled up to the size of a dying solar system and running without pause for 15 centuries, until the ordinary coolness of escaping gas has deepened into the coldest temperature ever measured anywhere. Here is that physics. When a gas expands, it cools. This is not a strange or exotic rule. It is the same reason that a can of compressed air turns frosty and cold when you spray it, or why the valve on a bicycle pump gets chilly as the air rushes out. When a gas is allowed to expand into a larger space, its particles spread out, they lose energy, and the temperature drops. Physicists call this adiabatic cooling, but you can just think of it as the chill of escaping air. Now imagine that same process, but instead of a can or a pump, the gas is the outer atmosphere of a dying star, and instead of a quick puff, the expansion has been going on relentlessly for 15 centuries. At the heart of the Boomerang Nebula is a star in its death throes, a star that was once something like our own sun, now shedding its outer layers into space. But it is not shedding them gently. This star is flinging its own substance outward at about 500,000 kilometers per hour, losing mass 10 to 100 times faster than other dying stars of its kind. That ferocious, high-speed outflow of gas is expanding into the surrounding darkness, and as it expands, it cools, by exactly the same rule that chills the air from a spray can. Except this outflow is so fast and so enormous, and has been running for so long, that it has driven the temperature of the gas down past every other cold place we know, down below the warmth of the universe itself, all the way to a single degree above the absolute floor. The Boomerang Nebula is not cold because it is empty and far from any fire. It is cold because it is an engine, a natural refrigerator built out of a dying star's last breath, actively refrigerating itself below the temperature of creation. Let me put you inside that idea for a moment, because it is stranger and lonelier than any furnace. Imagine drifting into the Boomerang Nebula. There is no scorching sky here, no wind of glass or metal. There is a faint glowing haze all around you, soft and pale, the shed skin of a dead star lit dimly from within. And it is quiet, and it is still, and it is colder than anywhere else that exists. The heat that fills the rest of the universe, the 2.7 degrees that reaches into every other corner of space, cannot keep up here. In this one place, the cosmos has been outrun. You're standing in the single spot in all of creation where the background warmth of the Big Bang has been beaten, where something has reached down past the floor of ordinary space toward the true and final cold. It is beautiful. It is the loneliest cold imaginable. I want to draw out why this belongs on a list of terrifying places, because at first it might seem like a curiosity rather than a horror. There is no violence here, no explosion, no obvious threat. But the Boomerang teaches something unsettling in a quieter register. It tells us that even the qualities we treat as fixed and final have a further extreme beyond them. We say space is cold, and we imagine we know what that means, that there is a bottom to it, the plain cold of the void, and then the universe shows us a place that fell straight through that bottom, that is colder than cold is supposed to be able to get out here. If even the temperature of empty space, one of the most basic and universal facts about the cosmos, can be beaten in some quiet corner, then what else that we assume is settled is actually just the middle of a range we have not finished exploring. The Boomerang Nebula is frightening not because it would hurt you, but because it proves the universe keeps a colder card in its hand than the one it shows. There is a reason nothing, anywhere, ever quite reaches absolute zero, and it deepens how remarkable the Boomerang really is. The laws of the quantum world forbid perfect stillness. Even at the very bottom of the temperature scale, particles retain a faint, irreducible trembling, a last shiver that can never be removed, which is why absolute zero is a limit that can be approached but never actually touched. So when we say the Boomerang Nebula sits at about 1 degree above absolute zero, we are saying it has crept almost all the way down to the floor that physics itself sets, closer than the leftover warmth of the entire universe is allowed to be. It is pressed right up against the coldest state that matter is permitted to occupy. And here is a quieter thought to carry away from this frozen place. The Boomerang is what astronomers call a young or preplanetary nebula, a very early stage in the death of a sun-like star, the first exhalation before the star fully sheds its outer layers and settles into a glowing shell. Which means the Boomerang is not only a picture of a strange and distant object, it is a picture of a future. Billions of years from now, our own sun will reach the end of its life, swell, and begin to cast off its outer layers into space, and for a time it too will be wrapped in an expanding, cooling shroud of its own making. It will not be as cold as the Boomerang, but it will be the same kind of event, the same slow, luminous dying. The coldest place in the universe is also a rehearsal for the eventual end of the star that keeps you warm. So far, every place we have visited has been about extremes of the ordinary, extreme heat, extreme cold, extreme wind. Frightening, but still within the family of things we can name. Now we are going to leave that family behind. The next place is not defined by a temperature or a weather system. It is defined by death, and by the strange and troubling fact that the very first other worlds humanity ever discovered, the first planets we ever found circling another star, were not new Earths waiting to be filled with life. They were graves, and they were orbiting a corpse. About 2,300 light-years away, in the constellation Virgo, there is a spinning corpse. It is the burned-out core of a star that died long ago, and it turns on its axis so fast that it is almost impossible to picture. It completes a full rotation every 6.2 milliseconds. That means it spins around roughly 160 times every single second. It is a city-sized ball of impossibly dense matter, whirling faster than the blades of any machine we have ever built, and as it spins, it sweeps beams of radiation across the sky like a lighthouse gone mad. This object is called PSR B.57+12, and it has been given a darker, more fitting nickname. It is called Lich, after the old word for an undead thing, a reanimated corpse that refuses to stay in its grave, and around this dead, spinning star there are planets. They were the first planets we ever found beyond our own solar system, and every one of them is a tomb. To understand why this place carries so much dread, you have to understand what Lich actually is, and to do that we have to talk about how it was born, because it was born in a catastrophe. Lich is a neutron star. It is what remains when a massive star reaches the end of its life and collapses. For most of its existence, a big star holds itself up against its own crushing gravity by burning fuel in its core, the outward push of that fire balancing the inward pull of its weight. But eventually the fuel runs out, and when it does, the balance fails in an instant. The core collapses in on itself, falling inward in less than a second, and the outer layers of the star detonate in a supernova, an explosion so bright it can briefly outshine an entire galaxy of billions of stars. What is left behind at the centre of that devastation is the collapsed core, squeezed so hard that its atoms are crushed out of existence and its matter is packed to almost unimaginable density. A neutron star holds more mass than our Sun inside a ball only about 20 kilometres across, the size of a city. A single teaspoon of its material would weigh billions of tons. This is the object at the heart of Lich. It is not a star in any warm and living sense. It is the compressed ash of a star that already died, and yet it has planets. 3 of them are known, and when astronomers gave them names they reached fittingly for the language of the undead and the haunted. The innermost, a tiny world only about 1/50th the mass of Earth, is called Draugr, after a creature from Norse legend that walks after death. The next, a world about 4 times the mass of Earth, is called Poltergeist, after a restless and troublesome spirit. The third, similar in size, is called Phobator, after a figure from Greek myth who brought nightmares. 3 worlds, orbiting a corpse, named for the things that come back from the dead and the dreams that terrify us. The people who named them understood exactly what they were looking at. Set this moment in its proper place in history, because the timing is part of what makes it so remarkable. For thousands of years, human beings had looked up and wondered whether other worlds circled other stars, and for all that time the question had stayed pure speculation, with no proof either way. Then, in the early 1990s, the silence finally broke, and the very first confirmed answer did not come from a warm and welcoming star like our own. It came from a pulsar, a spinning corpse, a lighthouse of radiation in the constellation Virgo. Of all the places the first exoplanets could have turned up, the universe chose to reveal them here, in orbit around a dead star, as if to warn us from the very beginning not to assume that other worlds would be anything like home. The discovery itself is one of the most important and least celebrated moments in the whole history of astronomy. In the year 1992, 2 astronomers, Alexander Wolszczan and Dale Frail, announced that they had found planets orbiting this pulsar. This was 3 years before anyone confirmed a planet around a normal Sun-like star. Let that sink in. The very first planets humanity ever discovered outside our own solar system, the first proof that other worlds exist at all, were not gentle blue Earths circling a warm and steady sun. They were dead worlds orbiting a dead star, drowned in radiation, spinning in the wreckage of an explosion. When we first reached out and found other planets, the universe handed us a graveyard. How did the astronomers even detect them? They could not see the planets directly. Instead, they watched the pulsar's beats. A pulsar like Lich sweeps its radiation beams past Earth with every rotation, and because it spins so precisely, those beats arrive with the regularity of the finest clock ever made, more regular than most atomic clocks we have built. But the beats were not perfectly regular. They arrived a tiny bit early, then a tiny bit late, in a repeating pattern. The only thing that could cause that was the gravity of unseen planets, tugging the pulsar in a small circle as they orbited, pulling it slightly toward Earth and then slightly away, shifting the timing of the beats. By reading those shifts, Wolszczan and Frail could weigh the planets and map their orbits without ever seeing them at all. They found worlds by listening to the heartbeat of a corpse and hearing it stumble. Now imagine standing on one of those worlds, on Poltergeist, say, the largest of them. Above you there is no warm sun. There is a small, dark, dense point in the sky, the neutron star, giving off almost no visible light. But it is not harmless. With every rotation, 160 times a second, its beams of high-energy radiation sweep across the landscape. The sky does not brighten with the comfort of dawn. It flickers with a lethal strobe, a lighthouse of particle radiation that would strip away any atmosphere and scour any surface. There would be no soft light, no warmth on your face, no sense of a day beginning. There would only be the dead star turning and turning and turning, throwing its poison across the graveyard worlds with every fraction of a second. This is not a place where life waits to begin. It is a place where the very idea of life has been sterilized by the death that made it. There is a detail here that turns the melancholy into something almost unbearable, and it is worth naming carefully. These planets probably did not exist before the star died. The supernova that created the neutron star would have destroyed or stripped away any worlds the original star once had. The planets we see now, Draugr and Poltergeist and Phobator, most likely formed afterward, out of the debris of the catastrophe, coalescing from the wreckage the way new things sometimes grow in the ruins of old ones. Which means these are not the surviving children of a dead sun. They are second-generation worlds built from the ashes, orbiting the very corpse whose death provided their raw material. They are graves standing on a grave. The first other worlds humanity ever found were monuments to a stellar death, assembled from its remains. I think it is worth sitting quietly with what that meant for us, as a species, at the moment of discovery. For all of human history, we had looked up and wondered whether there were other worlds, and whether they might be like ours, and whether we might not be alone. And the very first answer the universe gave us, the first confirmed planets beyond our sun, was this: a dead star, a killing strobe of radiation, 3 tombs named for the walking dead. It would be hard to design a more sobering reply to our hopeful question. The galaxy, it turns out, is not obligated to be full of homes. It is entirely capable of being full of graves, and when we first went looking, a grave is exactly what we found. The next time you hear someone say the universe must surely be crowded with living worlds, remember Lich, and remember what was actually waiting at the very first door we opened. To feel the full strangeness of Lich, you have to hold its 2 impossible extremes in your mind at once. On one hand, its material is so dense that a single teaspoon of it would weigh billions of tons, a spoonful heavier than a mountain, because it is matter-crushed until the empty space inside atoms has been squeezed away entirely. On the other hand, it keeps time more precisely than almost any clock humans have ever built. A millisecond pulsar like this one spins with such flawless regularity that its beats rival atomic clocks, ticking out across the galaxy with a steadiness that borders on the unreal. It is at once the densest kind of object we know and the most precise natural timekeeper we know, a crushed corpse that also happens to be a perfect clock. It was that perfect clock that gave the planets away. Because the beats arrive so regularly, astronomers could notice the almost imperceptible early and late pattern imposed by the tug of orbiting worlds, and from that pattern alone they weighed the planets and traced their orbits, all without a single image. There is a haunting irony buried in this. These graveyard worlds, orbiting a corpse and drowned in radiation, are among the most precisely characterized planets beyond our solar system, their masses and paths known with a confidence we cannot match for many far friendlier worlds. The first planets we ever found are still, in some ways, the most exactly measured, and they remain what they were the day we found them. Tombs, timed to the millisecond, circling the thing that killed everything that might once have lived near them. We have moved now from hostile weather to the aftermath of death, from worlds that would kill you to worlds where killing has already finished its work. But Lich is a death that is over. The explosion happened, the corpse is cold, the graveyard is quiet. The next place we are going is different. It is a death that has not happened yet. It is a star so enormous and so unstable that it has already tried to destroy itself once and somehow survived, and it is now sitting wrapped in the wreckage of that near death, waiting to finish the job. And the most unsettling part is that it may already have exploded, and we simply do not know it yet. About 7,500 light-years away, in the southern constellation of Carina, there is a star that is trying to die and cannot quite manage it. It is one of the most massive stars in our whole region of the galaxy, and it is one of the most unstable, and it has become a place of genuine dread among astronomers, because they know how the story ends. They simply do not know when. The star is called Eta Carinae, and to look at it now is to look at something caught in the instant before an explosion, an instant that has already lasted longer than a human lifetime, and might last another, or might end tonight. Wrapped around it, glowing, is the debris of the last time it tried to blow itself apart. Eta Carinae is a star wearing the wreckage of its own near-death and waiting to finish the job. Let me give you a sense of the scale of this thing, because everything about it runs past the edge of ordinary numbers. The main star at the heart of the system is roughly 90 times the mass of our Sun. That already places it among the true giants, because stars that heavy are rare and short-lived and violent. But the mass is not even the most frightening figure. Eta Carinae shines with something like 5 million times the luminosity of the Sun. 5 million. If you could set it where our Sun sits, it would flood the solar system with so much light and energy that the Earth would be sterilized in moments. Stars this massive live fast and die young. They burn through their enormous reserves of fuel in just a few million years, a cosmic eye blink compared to the 10 billion year calm of a star like ours, and then they end not with the quiet fade of a small star, but with the most violent explosions the universe produces. Keep in mind what a rare thing it is to catch a star at this exact stage. Most of the massive stars we study are either stably burning, with their violent ends still far in the future, or already gone, leaving only their remnants behind. Eta Carinae sits in the narrow, precarious window between, visibly unstable, actively shedding itself, poised on the threshold of its own destruction. Stars spend only a tiny fraction of their lives in this condition, which means that finding one close enough to study in detail is a genuine stroke of astronomical luck. We are watching, in real time, a phase that most stars pass through too quickly and too rarely for anyone to observe, and this one is doing it near enough for us to see every convulsion. And Eta Carinae has already given us a preview of its own violence. In the 1830s and 1840s, this star did something extraordinary. Between about 1837 and 1858, it underwent what astronomers now call the Great Eruption. It did not explode, not completely, but it convulsed. It threw off an amount of material somewhere between 10 and 40 times the mass of our entire Sun, hurling it out into space at speeds reaching 650 kilometers per second. To ordinary observers on Earth at the time, who had no idea what they were looking at, the effect was simply that a star grew brighter and brighter. By the year 1841, at the peak of the eruption, Eta Carinae had become the second brightest star in the entire night sky, outshone only by Sirius. And Sirius is one of our nearest stellar neighbours, a mere 8.5 light-years away. Eta Carinae achieved almost the same brightness from a distance of 7,500 light-years. It was blazing with the fury of a star tearing off its own outer layers, and it was doing it so brightly that people on the far side of the world could watch it happen with the naked eye, without ever understanding that they were witnessing a star nearly destroy itself. The Great Eruption itself must have been a bewildering sight for the people who witnessed it, and witness it they did, all across the southern hemisphere, without the faintest idea what they were seeing. Sailors used it to navigate. Observers noted it in their logs as one of the brightest stars in the sky, a new beacon that had climbed, seemingly overnight, near the very top of the list. None of them could have known that they were watching a single star thousands of light-years away tear off more than the entire mass of our Sun in a convulsion that would have vaporized any planet unlucky enough to orbit it. To the eye, it was simply a bright and beautiful star that had, for reasons no one understood, decided to blaze. The horror was invisible. Only the light reached them, gentle and lovely, carrying no hint of the violence that made it. What is left from that eruption is one of the most recognizable and haunting structures in the sky. The material Eta Carinae flung off did not disperse into nothing. It formed two enormous lobes of glowing gas and dust, an expanding hourglass shape now about 1 light-year long, with the tortured star sitting at the pinched waist in the middle. Astronomers call it the homunculus nebula, from a Latin word meaning little man, because in early images the shape suggested a small human figure. But there is nothing gentle about it. The homunculus is the shrapnel of a stellar convulsion, a shroud of debris that the star wrapped around itself in the act of nearly dying. Eta Carinae is not sitting in empty space. It is sitting inside the wreckage of its own last catastrophe, still glowing, still expanding, a monument to a death that was rehearsed but not completed. Now, let me pause here, because we are at roughly the middle of our journey tonight, and this is a good place to stop and look back at the ground we have covered, before we climb into the truly enormous places that make up the second half. Think about what terrifying has already come to mean over these 5 stops. It began as a matter of weather, with iron falling from the sky on a world too close to its star. Then it became a matter of deception, a beautiful blue planet that storms glass at 7 times the speed of sound. Then it became a matter of extremity, a nebula colder than the universe itself, proving that even the floor of cold has a basement. Then it became a matter of death and its aftermath, a graveyard of tomb worlds orbiting a spinning corpse. And now, with Eta Carinae, it has become a matter of timing, a death that has not yet happened, a fuse we can watch but cannot read. Each place has shifted the meaning of the word a little further from anything the human body was built to fear. We started with heat you could feel. We are moving toward horrors you can only understand, and we are not nearly finished. Because here is the part of Eta Carinae that keeps astronomers up at night, in the best and most curious way. Stars this massive do not survive their instabilities forever. Sooner or later, Eta Carinae is going to collapse and explode as a supernova, possibly even as a hypernova, an explosion at the extreme upper end of what stars can do. When that happens, it will be one of the great spectacles in the sky, bright enough to be seen in daylight, a new fierce point of light burning over the Earth for weeks or months. At its distance of 7,500 light-years, it is far enough away that the explosion, however spectacular, would pose no real danger to life on our planet. We would get the light show without the harm, but no one can tell you when it will happen. It could be 100,000 years from now. It could be next year. Massive dying stars keep their own schedule, and we have no way to read it. And this is where Eta Carinae delivers its final and strangest twist, the one that turns it from a distant curiosity into something genuinely vertiginous. Because the star is 7,500 light-years away, everything we see of it is 7,500 years old. The light reaching your eyes tonight left Eta Carinae around 5,500 years before the present day, back when the first cities on Earth were only just being built. Which means that the Eta Carinae we observe, the tormented star still wrapped in its glowing shroud, is a report from the distant past. The star as it truly is right now in this present moment is a mystery we cannot access. It may still be sitting there, unstable and waiting. Or it may have already exploded centuries or millennia ago, and the light of its death may be crossing the space between us at this very instant, a wave of brilliance that has not yet arrived. We could be living in the last years before Eta Carinae blazes across our sky. We could be looking at a star that no longer exists. There is no way to know, because the news travels at the speed of light, and the light is still on its way. Let me leave you standing in that uncertainty for a moment, because it is a peculiar kind of fear, one with no heat and no violence in it at all. Somewhere overhead, in the southern sky, there is a star that is going to detonate. That much is certain. The only thing hidden from us is the timing, and the timing may already have run out without our knowing. We are watching a delayed broadcast of a place that has quite possibly already ended, and when the true signal finally arrives, whenever it does, it will not be a warning of something to come. It will be the light of something that finished long ago, reaching us at last across 7,500 years of empty space. The particular menace of Eta Carinae comes from the kind of star it is, a rare and unstable class that astronomers call luminous blue variables. These are among the most massive stars that exist, and they live permanently on the edge of their own destruction, so bright and so heavy that the outward pressure of their own light is nearly enough to tear them apart from within. They flicker and surge unpredictably, and every so often they convulse, as Eta Carinae did in its great eruption, shedding great masses of themselves in a single paroxysm. The star is not even alone. It has a massive companion locked in orbit with it, and the two of them circle each other in a fraught, complicated dance that likely helped drive the eruption in the first place, two giants feeding a shared instability. When a star this massive finally dies, it does not fade. Its core collapses in an instant, and the collapse rebounds into a supernova, or possibly, for a star this extreme, a hypernova, an explosion at the very upper limit of what stars can do, the same kind of event that can, under the right conditions, fire off a beam of gamma rays like the one we worried about with the pinwheel star. Astronomers have even mapped the expanding homunculus in 3 dimensions, tracing every lobe and wrinkle of the debris the star has already thrown off, studying the wreckage the way investigators study the scene of a disaster that has not finished happening. Eta Carinae is a detonation caught in slow motion, its fuse already lit in a century we cannot read, and we are simply watching, from 7,500 years away, for the flash that may already be on its way. We have now spent the first half of our journey among worlds and stars, places with a shape and a location, things you could in principle fly to and orbit and name. Eta Carinae is a star that might already be a memory, but at least the danger it poses is a danger of a light and distance. The next place we're going brings a specific physical threat back into the picture, a real object that astronomers once feared might be a loaded gun pointed almost directly at the Earth. And the story of how they came to fear it, and then how they slowly talked themselves back down, is one of the best examples I know of how science actually handles a nightmare. About 8,400 light-years away, there is a shape in space that looks almost too neat to be natural. It is a spiral, a slowly turning pinwheel of glowing dust, curving outward in a smooth, elegant arc like water flung from a spinning garden sprinkler. It is genuinely beautiful, one of the most graceful structures we have ever photographed in the galaxy. And for a number of years, a great many astronomers looked at that beautiful spiral and quietly wondered whether they were staring straight down the barrel of a cosmic gun aimed almost directly at the Earth. The object is called WR104, and its story is the story of how science handles a nightmare by refusing to look away from it and then measuring it until the fear either proves itself or dissolves. These stars earn their fearsome reputation honestly. A Wolf-Rayet star has already burned through the outer layers that once cloaked it, and now it blazes with its searing inner self exposed, so luminous and so violent that it sheds mass at a furious pace, driving its own substance off into space in a ceaseless howling wind. Such stars are brief and rare, the short-lived final act of the most massive stars there are, and they exist in a state of barely contained fury. It is precisely this combination, enormous mass, furious spin, and a life teetering on the edge of collapse, that makes a Wolf-Rayet star one of the leading suspects for producing the most violent explosions the universe knows how to make. To understand the threat, you first have to understand the kind of star at the center of that pinwheel. It is a Wolf-Rayet star, and these are among the most extreme stars in existence, the exposed, furious cores of massive stars nearing the end of their lives. A Wolf-Rayet star has blown away its outer layers and now burns with such ferocity that it drives a constant hurricane of material off its surface, a stellar wind streaming outward at millions of miles per hour. In the case of WR104, this brutal star is not alone. It orbits a companion star, and that companion has its own powerful wind. Where the two winds slam into each other, they compress and heat the gas and forge dust, and because the two stars are orbiting one another, that dust gets wound up into a rotating spiral, the pinwheel we see. The elegance of the shape is a direct product of the violence that makes it. It is a beautiful pattern drawn by two dying stars tearing at each other's atmospheres. Now here is why anyone worried. Wolf-Rayet stars, especially fast-spinning ones, are considered leading candidates to produce the most powerful explosions in the entire universe, events called long-duration gamma-ray bursts. When a massive, rapidly rotating star of this kind finally collapses, it can, under the right conditions, channel an almost incomprehensible amount of energy into two narrow beams fired out along the star's spin axis from its north and south poles. A gamma-ray burst is not a gentle glow. In the few seconds that it lasts, it can release more energy than our sun will produce in its entire 10 billion year lifetime. But the crucial word is narrow. That energy is not sprayed in all directions. It is focused into tight beams, like the light of a lighthouse, and it only threatens whatever happens to lie along the line those beams are pointed. If you're off to the side, you may never even notice. If you're in the path, it is among the most dangerous things the cosmos can do. The unsettling part of the geometry was how clearly we seem to see the spiral. When we look at a pinwheel like this one and the whole graceful curve is laid out flat before us, it means we are looking down onto the plane in which the two stars orbit, roughly from above their shared pole. And the pole is exactly where the danger points, because a gamma-ray burst, if one ever comes, would be fired along the spin axis, straight out of that pole. So the very clarity of the beautiful spiral, the fact that we could see its shape so perfectly, was itself the reason for concern. Beauty and threat were, for a while, reading as the same thing, the clean face-on view that made the pinwheel photogenic being the same view that seemed to place us near the line of fire. And that is exactly what set off the alarm about WR104. because the pinwheel appears to us very nearly face-on. When we look at that graceful spiral, we seem to be looking down onto the flat plane of the two stars' orbit, which suggested that the spin axis of the system, the very direction along which any future gamma-ray burst would be fired, might be pointed close to our line of sight. In other words, if WR104 ever did produce a gamma-ray burst, and if its beam followed that spin axis, the Earth might be sitting somewhere near the firing line. Around the year 2008, this possibility was taken seriously enough to be studied and discussed, and inevitably dramatized. A burst aimed our way, even from 8,000 light-years off, could in principle strip away part of the Earth's protective ozone layer, exposing the surface to a flood of ultraviolet radiation from our own sun. The danger radius for such an event stretches across thousands of light-years, and WR104 was well within it. The star had become, in the public imagination, a Death Star, with the Earth possibly in its sights. Let me put you at the telescope in those years, because I think the human side of this matters. Imagine you are one of the astronomers studying WR104 in the late 2000s. Night after night, you resolve that lovely spiral in your instruments, and you know what it means. You know that somewhere inside that turning pinwheel is a star that could someday fire one of the universe's deadliest weapons. And you know that the geometry, as best anyone can measure it, suggests the barrel might be pointed somewhere near home. You cannot evacuate a planet. You cannot deflect a gamma-ray burst. All you can do is the one thing science ever really offers in the face of a nightmare, which is to look closer and measure better and refuse to let the fear outrun the facts. The whole discipline of astronomy, faced with a possible gun, did not panic and did not deny. It reached for a sharper instrument, and slowly the sharper instruments talked the fear back down. The astronomer Peter Toothill, who had first revealed the pinwheel nature of WR104 back in 1999, continued to study it, and his later work suggested the situation was far less alarming than the early worst case. He estimated the probability of any kind of dangerous gamma-ray burst event actually reaching us to be somewhere around the 1% level, and he cautioned that even that required more study. The system turned out to be more complicated than the simple face-on picture implied, and then, more recently, in the year 2025, new observations using instruments at the Keck Observatory in Hawaii refined the geometry further. They found that the orbit of the two stars is actually tilted by something like 30 to 40 degrees away from our line of sight, rather than pointing neatly at us. If the spin axis follows the orbit as expected, then any future gamma-ray burst from WR104 would most likely miss the Earth entirely, fired off into space in a direction that has nothing to do with us. I find this one of the most quietly reassuring stories in all of astronomy, and I want to be clear about why, because it matters for how you carry every other frightening thing on this list. The relief did not come from wishful thinking. Nobody talked themselves out of the fear by deciding it was too scary to be true. The relief came from arithmetic, from years of patient measurement, from tilting the instruments a little more precisely and letting the numbers speak. WR104 was a genuine candidate for a real threat, and science treated it as one, and then science measured it carefully enough to largely stand it down. That is the pattern worth trusting. When you hear that some object in the sky might be dangerous, the right response is not terror and not dismissal. It is exactly what the astronomers did here. Look closer, measure better, let the data decide. More often than not, the careful measurement is the thing that lets you sleep. There is one more reason WR104 belongs on this journey, beyond the drama of the near miss. It is a reminder that the sky is not a settled catalogue of known quantities. It is an ongoing investigation. The threat assessment of this one object changed over the course of less than 2 decades, from serious concern in 2008 to careful caution a few years later to considerable relief by 2025. The universe did not change, our knowledge of it did, and that is happening all the time across thousands of objects as our instruments improve and our understanding deepens. Some fears will grow, others, like this one, will shrink. The pinwheel keeps turning out there, beautiful and indifferent, and we keep watching it, and for now, the gun appears to be pointed somewhere else. It helps to grasp just how much energy a gamma-ray burst actually represents, because the number is what turns a distant star into a genuine concern. In the few seconds that a long gamma-ray burst lasts, it can pour out more energy than our sun will radiate across its entire 10 billion year lifetime, all of it focused into those 2 narrow beams. If one of those beams swept across a nearby world, the effect would not be to incinerate the planet directly from thousands of light-years away. It would be subtler and more insidious. The blast of gamma rays would tear apart the molecules high in the atmosphere, wrecking the ozone layer that shields the surface, and leaving whatever lived below exposed to a flood of ultraviolet radiation from its own sun for years afterward. The killer would not be the burst itself so much as the loss of the shield it destroyed. Some scientists have even proposed that a gamma-ray burst may have played a role in one of the great mass extinctions in Earth's own distant past, hundreds of millions of years ago, though this remains a hypothesis rather than an established fact. What is certain is that a well-aimed nearby burst would be dangerous, and that is exactly why the geometry of WR104 mattered so much, and why the careful measurement of its tilt brought such relief. The reassuring truth, when you add it all up, is that a burst close enough and aligned precisely enough to harm us is genuinely rare. The galaxy is enormous, the beams are narrow, and the odds of one lining up with our small world are slim. WR104 was worth studying precisely because it seemed, for a while, to beat those odds, and it is worth remembering because, on closer inspection, it did not. We have now reached a turning point in our countdown. Everything so far, the worlds of iron and glass, the frozen nebula, the graveyard pulsar, the waiting supernova, the Death Star pinwheel, has been dangerous at a distance, or dangerous by accident, or dangerous only in the future. But the next place is different. It is an object that is actively right now, in this moment, destroying another star. It is a black hole, the first one humanity ever found, and it is close enough that we can watch it feed. And once we arrive there, we will have left behind the worlds and the stars entirely and begun our descent toward the thing at the very bottom of this list, the place with no way out at all. About 7,200 light-years from here, in the constellation of Cygnus, the Swan, there is a place where a living star is being slowly unravelled and swallowed. It has been happening the entire time our species has existed. It was happening when the first humans looked up and named the stars, and it is happening tonight, and it will go on happening long after we're gone. There is a black hole here, and it is not sitting quietly in the dark. It has a companion, a great blue star, and it is pulling that star apart, thread by glowing thread, drinking its substance down into a place from which nothing returns. This object is called Cygnus X1, and it holds a special place in the history of science because it was the first object anywhere that humanity became convinced was actually a black hole. Before we watch it feed, let me remind you what a black hole really is, because the words get used so often that they can lose their weight. A black hole is a region where matter has been crushed so completely, and gravity has become so intense that beyond a certain boundary nothing can escape, not even light. That boundary is called the event horizon, and it is not a surface, not a wall you could touch. It is a line in space that marks the point of no return. Cross it, and every possible path leads inward. Light itself, the fastest thing there is, cannot climb back out. This is why a black hole is black. It is not a dark object sitting in space. It is a place where the escape routes have been closed, a one-way door in the fabric of the universe. Cygnus X1 was the first such door we ever felt confident we had found. The discovery unfolded over years. In the 1960s, instruments carried above the atmosphere detected a powerful source of X-rays coming from the direction of Cygnus. X-rays are a form of light far more energetic than the light our eyes can see, and they tend to be produced by matter that has been heated to extraordinary temperatures. By the early 1970s, astronomers had worked out that this X-ray source was paired with a visible blue supergiant star, a massive luminous star catalogued with the designation HDE 226868. But the blue star alone could not explain the X-rays. Something else was there, something invisible, something with enormous mass, locked in orbit with the supergiant. As the measurements tightened, the conclusion became harder and harder to avoid. The invisible companion was too massive to be a dead star of any ordinary kind, too small and dark to be a normal star at all. It had to be a black hole, and the X-rays were the sound of it eating. There is something almost intimate about the closeness required for this theft, and it deepens the horror rather than softening it. The black hole and the supergiant are not distant strangers. They are bound partners, orbiting one another, close enough that the black hole's gravity can reach across the gap and lay hold of the outer atmosphere of the living star. In a sense, the two have been locked together since they were born, a massive star and the collapsed corpse of its even more massive sibling, circling in a relationship that can end only one way. The living star cannot pull free, it cannot flee. It is held in orbit by the very object that is consuming it, close enough to be fed upon and far too close to ever escape, giving up its substance to a partner it can neither leave nor survive. Here is how the eating works, and it is a genuinely eerie process. The black hole and the blue supergiant orbit close together, close enough that the black hole's gravity reaches out and grips the outer layers of the living star. It peels gas away from the supergiant, drawing a stream of stellar material across the gap between them. But that gas does not fall straight in. Because everything is orbiting, the stolen material spirals inward, forming a flattened, whirling disk around the black hole, like water circling a drain. This is called an accretion disk, and as the gas spirals in, it is compressed and sheared and heated by friction to millions of degrees, so hot that it blazes in X-rays, screaming out radiation in its final moments before it crosses the event horizon and vanishes forever. Those X-rays, the ones our instruments caught back in the 1960s, are the death cries of matter being torn off a star and swallowed by the dark. The glow we detect is the last light of gas that is about to stop existing, as far as our universe is concerned. These measurements did not come easily. Pinning down the mass of a black hole you cannot see means tracking the motion of its visible companion with extraordinary precision over years and combining that with an exact distance, which is one of the hardest things in all of astronomy to measure. The team used a technique that watches how the position of the system shifts against far more distant background objects as the Earth moves around the Sun, a tiny wobble that reveals the true distance. Only after nailing that distance could they be confident about the masses. The result was a black hole heavier than anyone had thought, and a victim star heavier too, a pairing of giants refined by some of the most painstaking measurement our instruments can perform. In 2021, a team of astronomers led by James Miller Jones used precise radio measurements to update our picture of this system, and the numbers grew more menacing. The black hole turned out to be about 21 times the mass of our Sun, more massive than earlier estimates had suggested. Its companion, the blue supergiant it is devouring, is a genuine monster in its own right, around 40 times the mass of the Sun. Picture that. A star 40 times heavier than our Sun, one of the brightest and most powerful kinds of star there is, and it is the victim in this story. It is the one being consumed. There is something almost unbearable about the scale of it. A star that would dwarf our Sun, that would flood our solar system with light, reduced to a food source, its outer layers streaming steadily away into a hole in space, a little more gone with every passing year. Let me put you there, at a safe and impossible distance, and let you watch. In front of you hangs the blue supergiant, huge and radiant, its surface roiling, and reaching away from it, drawn out by an invisible pull, is a bright streamer of gas, arcing across the darkness toward a point you cannot see directly. Follow that streamer with your eye. It spirals inward, coiling into a fierce glowing disk that whirls faster and hotter as it narrows, shining in colours your eyes were never built to catch. And at the very centre of that blazing disk is a small circle of absolute black, a hole in the light, and the gas pours toward it and reaches the edge and simply stops being there. Not consumed in fire, not scattered. Gone, across a boundary that leads only one way. You're watching a star die, not in an explosion, but in a slow theft that has no end, a great blue sun being drained one thread of light at a time. I want to sit with the emotional weight of this, because I think it is the heart of why Cygnus X1 unsettles me more than the abstract giants we sometimes talk about. We speak of black holes so casually, as concepts, as physics problems, as scary ideas. But this is not an idea. This is a specific place, in our own galaxy, close enough that we found it more than 50 years ago, and there is a named star there, a real one, 40 times the mass of our Sun, and it is being eaten alive, and it has been the entire time you have been alive, and the entire time your parents and their parents were alive. Every fear on this list becomes something different when it stops being a category and acquires an address. Somewhere out there, in the direction of the Swan, a star is dying by inches, and it will still be dying long after everyone who ever read a word about it has passed away. Horror is one thing when it is a possibility. It is another thing entirely when you can point to the exact spot in the sky and say, there, it is happening there, right now. There is a wonderful piece of human history attached to this object, and it lightens the dread just enough to be worth telling. The physicist Stephen Hawking, who spent much of his life thinking about black holes, made a famous bet with his friend and fellow physicist Kip Thorne. Hawking bet that Cygnus X1 was not, in fact, a black hole. He explained with characteristic humour that this was a kind of insurance policy. He had invested so much of his career in the theory of black holes that if they turned out not to exist, at least he would win the bet and have something to console him. But as the years passed, the evidence that Cygnus X1 truly was a black hole became overwhelming, and in 1990 Hawking conceded the bet. He had, in a sense, hoped to be wrong, and the universe had insisted he was right. The first black hole we ever found was real, and it was hungry, and even one of the greatest minds of the century could not wish it away. It is worth understanding where a black hole like the one in Cygnus X1 even comes from, because its origin is its own kind of horror. This black hole, 21 times the mass of our Sun, is the collapsed remnant of a massive star that reached the end of its life and fell in on itself so completely that not even light could escape the result. Its companion, the blue supergiant, is walking the same road. It too is a massive star burning through its fuel at a furious rate, and it too will one day collapse and die. The system is, in a sense, a preview of its own future, one partner already fallen into darkness, the other still shining but doomed to follow. Two giants, one of them already a corpse that eats, the other still alive and feeding it. The reason the theft glows in X-rays comes down to speed and friction. As the stolen gas spirals inward, it is forced to move faster and faster, and the inner parts of the whirling disk drag against the outer parts, heating the material through sheer friction to temperatures of millions of degrees, far hotter than the surface of any ordinary star. Matter that hot does not shine in visible light. It screams in X-rays. And because that X-ray glow flickers and changes on timescales of mere fractions of a second, astronomers could work out that the region producing it must be extraordinarily small, smaller than our solar system, exactly what you would expect from gas swirling down toward an object only a few dozen kilometers across. Decade after decade, the observations have only tightened, and the conclusion has never wavered. There is a real black hole in Cygnus, and it has been eating a living star through the whole of recorded human history. We have now left the worlds and the stars behind, and stepped through the first true door in the fabric of space. But Cygnus X1, terrifying as it is still a single object, a local horror with a fixed location you could fly toward or away from. The next place is something else entirely. It is not an object at all. It is a direction. It is the discovery that our entire galaxy, and everything in it, including you, is being pulled towards something so large and so hidden that we cannot even see it properly. We are all falling right now, and we cannot feel it, and we cannot stop it. Right now, without any sensation at all, you are moving. Not the gentle spin of the Earth on its axis, though that is happening too. Not the yearly loop of the Earth around the Sun, though that is happening as well. Not even the long, slow circle our Sun makes around the centre of the galaxy. Beyond all of those familiar motions, our entire galaxy, the whole Milky Way with its hundreds of billions of stars, is falling. It is being pulled through space towards something at a speed that is difficult to hold in the mind, and it has been falling for as long as it has existed, and nothing will ever slow it down. The destination has a name. Astronomers call it the Great Attractor, and the sharpest unease of this place is that we still cannot properly see what is pulling us. Let me give you the speed first, because the speed is the part that makes it real. Our local group of galaxies is moving at roughly 630 kilometers every second, relative to the ancient background glow of the universe. 630 kilometers per second works out to about 2.2 million kilometers per hour. At that pace, we cover something like 63 light-years of space every year, and there is no engine doing it, no force you could switch off. It is gravity, the accumulated pull of enormous amounts of matter, drawing us steadily in one particular direction, and we are simply falling the way a dropped stone falls, except the fall never ends and the ground never arrives. Now here is the first strange thing. You cannot feel any of it. There is no wind, no rush, no sense of speed. When you fall freely under gravity, everything around you falls together, and so there is no sensation of falling at all. The astronauts orbiting the Earth are not floating because there is no gravity up there. They are floating because they are falling continuously, and everything in their spacecraft falls with them. We are in exactly the same situation, on the scale of a galaxy. The whole Milky Way is in free fall toward the Great Attractor, and because everything falls together, every star and every planet and every atom, we feel perfectly still. You could not detect this motion by any sensation in your body. We only know it is happening because we can compare our movement against the faint, even glow of radiation left over from the birth of the universe, and see that we are sliding through it, all of us together, toward one spot in the sky. First, let the speed sink in one more way, because it is easy to read a number and not feel it. 630 kilometers every second means that in the time it takes you to draw a single slow breath, you and your entire galaxy have moved several thousand kilometers through the universe, farther than the distance across a continent, and then several thousand more with the next breath, and the next, without pause, without end. Every moment of your life, awake or asleep, you have been carried this way, and so has everyone who ever lived, and so has every star anyone has ever named. It is the largest motion you are part of, and it is utterly, perfectly silent. And what is at that spot? This is where the fear sharpens into something specific. The Great Attractor is a gravitational focus, a concentration of mass, sitting about 150 to 250 million light-years away, in the direction of the southern constellations of Norma and Centaurus. It lies near the centre of our home supercluster, an enormous collection of galaxies that astronomers, in 2014, mapped and named Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea stretches across about 520 million light-years, and it contains our Milky Way as one tiny member among many thousands of galaxies, all of them flowing, like water running downhill, toward the basin at the centre. The Great Attractor sits near the bottom of that basin. We are one drop in a current of galaxies, all pouring toward the same low point. But here is the part that has haunted astronomers for decades. We cannot get a clear look at the Great Attractor, because it lies almost directly behind the plane of our own galaxy. When we try to look in that direction, our view is blocked by the dense clouds of stars, gas, and dust that make up the disk of the Milky Way itself. Astronomers call this blocked region the zone of avoidance, because it is the part of the sky that optical telescopes have to avoid, the region where our own galaxy stands in the way. So the thing that is pulling us, the destination of our billion-year fall, is hidden behind a curtain of our own making. We can feel its pull. We can measure our motion toward it with great precision. But when we turn to look it in the face, our own galaxy's body is in the way. We are being drawn toward a place we are structurally unable to see. For a long time, the Great Attractor was the whole story, an unseen mass pulling us in. But in the year 2017, a team of astronomers led by Yehuda Hoffman and Brent Tully added the other half of the picture, and it made the situation stranger and somehow more complete. They found that our motion is not only a matter of being pulled, it is also a matter of being pushed. On roughly the opposite side of the sky from the Great Attractor, they identified an enormous region that is emptier than average, a great underdense void where there are far fewer galaxies than there should be. They called it the dipole repeller, and because gravity is only ever a pull, a region with less matter than its surroundings effectively repels, in the sense that everything is drawn away from the emptiness and toward the fuller regions on the far side. So we are caught between two influences. On one side, the Great Attractor and the great masses beyond it pull us in. On the other side, the emptiness of the dipole repeller pushes us away. Pulled from ahead, shoved from behind, our galaxy slides steadily across the universe, carried by the combined hands of what is full and what is empty. And the destination goes further still. Beyond the Great Attractor, further along the same direction, lies an even more massive concentration of galaxies called the Shapley supercluster, one of the largest structures in the nearby universe. Much of our long fall is ultimately toward that greater mass, with the Great Attractor as a way station along the road. We are not simply drifting. We are being drawn into the largest gravitational features in this entire region of the cosmos, a journey measured not in years or centuries, but in the slow gravitational time of galaxies, a fall that began before the Earth existed and will continue long after it is gone. Let me ask you to do something, right where you are lying. Hold still. Feel how still you are. The bed beneath you, the floor, the walls, the ground under the building, all of it feels perfectly, reassuringly motionless. And now, hold in your mind the truth of it. You're not still at all. You, and the bed, and the building, and the entire planet, and the sun, and every star you have ever seen with your own eyes are moving together through space at over 2 million kilometers an hour toward a place hidden behind the body of our own galaxy, a place no human eye has ever clearly seen. You're covering 63 light years every year, and you cannot feel a single kilometer of it. There is no wind in your face. There are no brakes to reach for. There is no steering. The most enormous motion you are part of is the one you will never sense, a silent fall that carries everything you have ever known toward a destination you were not consulted about and cannot change. I think this is a different flavor of fear from anything we have touched so far tonight, and it is worth naming precisely, because it is a fear about control rather than about harm. The Great Attractor will not hurt you. The fall is gentle, imperceptible, spread across timescales so long that nothing in a human life is affected by it in the slightest. And yet there is something in it that reaches straight into a very old part of us, the part that wants to believe we are steering, that we have a say, that the ground beneath us is fixed. The Great Attractor quietly removes all of that. It tells you that the largest journey of your existence, the movement of your entire galaxy across the universe, is happening without your knowledge, without your permission, and without any possibility of your ever affecting it. You are a passenger on a vessel with no windows facing forward, falling toward a shore you cannot see. And here is the thing to hold on to as we move toward the final places tonight, because it changes the character of the fear. Every place we have visited so far you could in principle leave. You could fly away from the iron rain, steer clear of the glass storms, keep your distance from the pulsar and the dying star and the feeding black hole. Even here, in the great fall toward the attractor, you are still free to move about within the current, to fly this way or that inside the falling galaxy. The fall takes your galaxy, but it does not take your freedom to move. That freedom, the simple ability to go somewhere else, is something we carry with us everywhere, so automatically that we never notice we have it. Keep it in mind, because there is exactly one place left on this list where that freedom does not exist, where there is no somewhere else to go, and we are almost there. The pull we feel was noticed long before anyone had a name for its source. Back in the 1970s, as astronomers began carefully measuring the motions of galaxies, they realized that our own galaxy and its neighbors were not simply drifting along with the general expansion of the universe. They were streaming in a coordinated bulk flow toward one particular region of the sky, as though caught in an immense current. It took decades of work to map that current and to identify the great concentrations of mass responsible for it. And even now, with the zone of avoidance hiding so much of the view, the full accounting is not complete. Much of the mass doing the pulling is not even the glowing matter of stars and galaxies. It is dark matter, the invisible substance that outweighs ordinary matter several times over and provides most of the gravity holding the larger structures together. We are being pulled, in large part, by something we cannot see, made of a substance we have never identified, toward a place our own galaxy blocks from view. There is one strange mercy folded into all of this, and it comes from the expansion of the universe itself. As space stretches ever faster, driven by the mysterious dark energy that is pushing the cosmos apart, the great structures beyond our immediate neighborhood are slowly being carried out of reach. In the far future, the pull of the Great Attractor may be overwhelmed by that expansion, so that we never actually arrive, forever falling toward a destination that recedes just ahead of us. It is a peculiar kind of comfort, if you can call it that. The current is real, and the fall is real, and yet the shore may quietly dissolve before we ever reach it, leaving our galaxy adrift in an expanding emptiness, still falling, forever, toward a place that is no longer there. But before we reach it, we have to pass through the most crowded, most violent, most dangerous neighborhood in our entire galaxy. It is the place our own solar system was lucky enough to be born far away from. It is the downtown of the Milky Way, the dense and blazing core where the stars are packed so tightly that night would never fall, where they whip around a central monster at a fraction of the speed of light, and where wandering too close means being torn apart. That is our 9th place, and it is the last stop before the door at the bottom of everything. About 26,000 light-years from here, at the very center of our galaxy, there is a place that makes everything around us look like a peaceful country field at the edge of a quiet town. We live out in the suburbs of the Milky Way, on a calm spiral arm, in a sparse and gentle stretch of space where the nearest star to our Sun is more than 4 light-years away, and the sky between the stars is mostly empty dark. We think of that as normal. It is not normal. It is a rare and fortunate accident. The true heart of our galaxy is nothing like it. The galactic centre is the most crowded, most radiation-soaked, most violent neighbourhood in the entire Milky Way, and if our solar system had formed there instead of out here, life on Earth would very likely never have had the chance to begin. At the exact centre sits a supermassive black hole called Sagittarius, a star, weighing about 4 million times the mass of our Sun. In the year 2022, astronomers using a worldwide network of telescopes managed to capture an actual image of it, a dark circle ringed by the glow of superheated gas, the second such portrait of a black hole ever made. But tonight I do not want to focus on the black hole itself, because we are saving the true horror of black holes for our final stop. What I want you to feel here is the neighbourhood around it, the environment, the sheer terrifying density of the place. Because the danger of the galactic centre is not just the monster at its heart, it is the whole blazing, overcrowded district that surrounds it. Begin with the black hole's own scale, just enough to set the stage. 4 million times the mass of the Sun is a genuinely enormous amount of matter to gather into a single point, and its gravity dominates the entire central region, ruling the motions of everything for many light-years around. But a supermassive black hole, for all its power, is quiet when it is not feeding, a dark and patient presence rather than an active threat. What makes the neighbourhood lethal is not the black hole sitting still at its centre. It is everything the black hole has gathered around itself over billions of years, the dense swarm of stars, the clouds of gas, the constant traffic of objects on steep and dangerous orbits, all of it packed into a space that in our quiet suburb would hold almost nothing at all. Consider how packed the stars are near the centre. Out here in our quiet suburb, the space around us is nearly empty, with light-years of darkness separating one star from the next. In the central region of the galaxy, the stars are crammed together at a density perhaps 10 million times greater than in our neighbourhood. 10 million times. If Earth orbited a star near the galactic centre, our night sky would not be a scattering of faint points on black. It would blaze. Thousands upon thousands of brilliant stars would crowd the heavens, many of them brighter than the full moon, filling the sky with so much light that true darkness would never come. There would be no night as we understand it, no true dark for sleeping, no faint and distant stars, only a permanent crowded glare of neighbouring suns pressing in from every direction. The gentle darkness you're resting in right now is a luxury of the suburbs, and the stars near the centre do not sit still and peaceful. They move. In the innermost region, a group of stars known as the S-cluster orbits the central black hole in tight, fast-whipping loops. One of them, a star called S2, has been tracked for decades as it races around Sagittarius A star, completing a full orbit in only about 16 years. Think about that. A whole star, larger than our Sun, swinging around the black hole in less time than it takes a human child to grow up. At its closest approach, S2 comes within about 17 light-hours of the black hole, and as it rounds that closest point, it reaches a speed of roughly 7,700 kilometers per second. That is about 2.5% of the speed of light. There is a star at the center of our galaxy moving fast enough that, if you watched it long enough, you could actually see it shift its position against the sky, a sun flung around a dark heart at a fraction of light speed. Nothing in our calm neighborhood moves remotely like that. Now add in what happens when something wanders too close. The central black hole is not always feeding, but every so often a star or a great cloud of gas drifts too near, and when it does, the black hole's tidal gravity tears it apart. Astronomers call this a tidal disruption event. The doomed star is stretched and shredded, pulled into a long streamer of glowing debris, and as that material spirals in and heats up, it can briefly flare so brightly that it outshines the combined light of all the billions of stars in the galaxy's core. These are among the most dramatic events in the entire galaxy, a star being ripped to pieces and its remains set ablaze, and they happen, on cosmic timescales, again and again at the centre. To live near there would be to live in a place where the sky periodically erupts with the death of a neighbouring star, and over all of this hangs radiation. The dense core of the galaxy is flooded with high-energy light and fast-moving particles. From the crowded stars, from the material falling toward the black hole, from the violent processes constantly unfolding in that packed space. Far above and below the galactic center, astronomers have found two enormous structures, towering bubbles of hot gas and energetic particles reaching tens of thousands of light-years out from the core. These are called the Fermi bubbles, and they are thought to be the fossil evidence of some tremendous past outburst from the galactic center, a time when the black hole or the region around it erupted with enough energy to blow these titanic bubbles into space. The center of our galaxy is not a stable, quiet place that has always looked the way it does now. It is a place with a violent history written across the sky above and below it, a place that has erupted before and may well erupt again. Put it all together and imagine trying to survive there. The sky never darkens, blazing with the light of millions of crowded stars. Nearby suns swing past at a fraction of light speed, their gravity occasionally flinging worlds out of their orbits or dragging them into chaos. Radiation soaks everything, enough to sterilize a planet's surface and strip away its atmosphere over time, and every so often the central monster tears a star apart and lights the whole core with the flare of its dying. This is not a place where a fragile, slow miracle like life could get comfortable for the billions of years it took to produce anything as complicated as the creature reading these words. The stability that life needs, the long, uninterrupted calm, simply does not exist in the downtown of the galaxy. It exists out here, in the quiet, in the sparse and gentle suburbs, in exactly the kind of unremarkable neighborhood we happen to call home. I think this is the quietest and most important lesson of the entire journey, and it arrives right before the end for a reason. We tend to assume that our situation is ordinary, that a calm night sky and a stable orbit and a planet left alone for billions of years is simply how things are. But the tour we have taken tonight says otherwise. The calm is the exception. Across the galaxy and beyond it, the default settings run toward the hostile, the crowded, the violent, the lethal. The universe is entirely capable of raining iron, storming glass, freezing below the temperature of creation, drowning worlds in radiation, tearing stars apart and swallowing them whole. Our gentle corner, with its empty dark and its stable sun and its long, uninterrupted quiet, is not the rule that the frightening places break. It is the rare and precious exception, the unlikely pocket of calm in which something like us could slowly, patiently come to exist. We did not end up somewhere safe by right. We ended up somewhere safe by luck. It is worth lingering on just how routinely violent the galactic center is, because the violence is not a rare accident there. It is the ordinary weather. Every so often a star or a great cloud of gas is drawn too close to the central black hole and torn apart, and astronomers have watched these tidal disruption events flare across the sky, brief and blinding as the shredded remains blaze on their way down. Not long ago they tracked a cloud of gas making a close pass by the black hole, holding their breath to see whether it would be devoured, studying the encounter in real time. The inner region is a place where the machinery of destruction is always running, where the tearing apart of stars is not a story from the distant past, but an ongoing process you could, in principle, sit and watch. And this is the truest reason our quiet suburb matters so much. Life, as far as we understand it, needs time, enormous stretches of uninterrupted time, billions of years of stability for something as intricate as a thinking creature to slowly assemble itself. The galactic center offers no such peace. Between the crowding, the radiation, the wandering stars, the frequent nearby explosions, and the ever-present threat of the central monster, no world there could hold still and safe for the ages that life requires. Our own solar system has enjoyed roughly 4.5 billion years of near-perfect calm, undisturbed, out here in the sparse and gentle dark, and that calm is the true reason you exist at all. We're not merely lucky to have avoided the center. We're alive because we did. And now we come to the last place. We have travelled outward from worlds, to corpses, to dying stars, to black holes, to the great falling motion of the galaxy, to the blazing danger of its core. At every single stop, no matter how terrible, one thing has quietly remained true. You could always, in principle, leave. There was always a somewhere else, a direction called away, an escape route however difficult. That freedom to leave is the one thing every place on this list has still allowed you to keep. The final place takes it. It is the one location in the entire universe where away is not a direction you can travel, where the exit is not merely blocked but erased from reality itself. It is time to go inside a black hole. The nearest confirmed black hole to Earth is called Gaia BH1, and it sits about 1,560 light-years away, in the direction of the constellation Ophiuchus. It was discovered only recently, in the year 2022, and it is a quiet one, a dormant black hole about 10 times the mass of our Sun, not feeding, not blazing with X-rays, simply drifting through space with a Sun-like companion star orbiting it every 185 days. Astronomers found it not by any light it gives off, because it gives off none, but by watching the way its companion star swung back and forth, tugged by the gravity of something massive and invisible. Gaia BH1 makes a useful nearest door, the closest such object we know of, but I did not save black holes for last because of the door. The door is just an object, a place you could fly toward or away from like any other. I saved this for last because of what lies on the other side of the door. Because the most terrifying place in the entire universe is not any black hole you can point to from outside. It is the region within one, past the boundary, and it is terrifying for a reason unlike anything else on this list. Let me tell you what actually happens as you approach and cross that boundary, because it is stranger than the movies suggest, and the strangeness is the whole point. The boundary of a black hole is called the event horizon, and here is the first surprise. It is not marked. There is no wall, no membrane, no shimmering surface, no sudden jolt. If you were falling toward a large enough black hole, you could cross the event horizon without noticing anything at all in the moment you did it. Space right at the horizon looks like ordinary empty space. You would drift across an invisible line in the vacuum, an unremarkable stretch of nothing, and in that instant everything would change, and nothing would feel different. There would be no signpost telling you that you had just passed the most important boundary in the universe. You would simply be inside, and outside would be gone forever. It is worth being precise about why nothing can return, because it is not the answer most people expect. The usual picture is that a black hole's gravity is simply so strong that you cannot pull away from it, the way you might fail to climb a hill that is too steep. But that is not quite the truth. The truth is stranger. It is not that the exit is too hard to reach. It is that, past the horizon, there is no exit to reach, because the warping of space and time has bent every possible route so that all of them lead inward. Firing your engines harder does not help, because there is no longer any direction that points out. You're not being held down by a force you might, with enough power, overcome. You're trapped by geometry itself, by the shape reality has taken in that place, and geometry is not something you can push against. Because that is what the event horizon is. It is the surface of no return. It is defined as the boundary beyond which no path leads back out, not for a spaceship, not for a beam of light, not for anything. Outside the horizon, if you fire your engines hard enough, you can still climb away, still escape the black hole's grip. Inside, no amount of power, no speed, no ingenuity, nothing that could ever exist can carry you back across that line. And the reason is not that the pull is simply very strong, the way you might struggle against a powerful current and eventually tire. The reason is far stranger and far more disturbing than mere strength. Inside the event horizon, the geometry of space and time themselves have been so warped that every possible direction you could move, every path your body could take, leads inward, toward the center. Out is no longer a place you can go. It is no longer one of the directions that exists. I want to slow down here, because this is the single strangest and most important idea in all of physics about these places, and it is the thing that makes a black hole's interior different in kind from everywhere else we have been. Outside a black hole, in the ordinary universe where you and I live, space is the thing you can move around in freely in any direction, and time is the thing that carries you relentlessly forward, always into the future, never back into the past. You can choose to walk east or west, up or down, but you cannot choose to stop moving toward tomorrow. Tomorrow comes whether you want it or not. That is the normal arrangement. Space is where you are free. Time is where you are carried. Inside the event horizon, according to the mathematics of general relativity, those two things trade places. The direction pointing toward the center of the black hole, toward the singularity at its heart, stops behaving like a direction in space and starts behaving like the direction of time, which means that falling toward the center becomes exactly as unavoidable as falling toward tomorrow. The singularity is not a place sitting somewhere ahead of you that you might steer around with a clever enough maneuver. It becomes a moment in your future, as fixed and inescapable as next Tuesday. You cannot avoid the center of a black hole for the same reason you cannot avoid the passage of time. It is not in front of you in space, it is ahead of you in time, and nothing anyone has ever imagined can stop you from arriving. Before we go deeper, hold on to how ordinary the approach would feel, because that ordinariness is part of the dread. For a large black hole there is no dramatic threshold, no shuddering barrier, no alarm that sounds as you near the horizon. The stars ahead of you would simply bend and crowd together around a growing circle of black, and space would look, right up until the boundary, like perfectly normal space. You could cross the most absolute frontier in the universe, the line past which return is not merely hard but impossible, in a state of complete calm, unaware that anything had happened. The trap does not slam. It closes without a sound, in a place that looks like nowhere in particular, and that is exactly why it is so complete. There is a physical price for the journey too, and it has a strangely gentle name for such a brutal thing. Astronomers call it spaghettification. As you fall toward a black hole, the pull on the part of your body nearer the center is stronger than the pull on the part farther away. This difference stretches you, lengthwise, head to foot, while at the same time squeezing you inward from the sides, so that you're drawn out into a long, thin strand, like a piece of dough pulled into a noodle. For a small black hole, this stretching becomes lethal before you even reach the horizon. For a truly enormous one, the difference is gentle at first, and you could cross the horizon still whole, still yourself, only to be stretched without mercy as you fell deeper toward the center. Either way, the ending is the same. Everything that falls in is drawn down toward the singularity, that point where our understanding of physics itself breaks down, where the mathematics predicts infinite density, and then stops being able to tell us anything at all. It is, quite literally, the edge of what we know. The deepest part of the most terrifying place in the universe is also the place where our best theory of gravity throws up its hands and admits it can no longer follow. Let me put you inside the fall now, one last immersive descent, because I want you to feel the shape of this before we step back out into the light. Imagine you are falling toward Gaia BH1, that quiet, dark, 10 solar mass companion in the constellation Ophiuchus. Ahead of you is not a hole, not a funnel, but a perfect circle of absolute black against the stars, ringed by a thin distortion where the light of the sky behind it is bent and smeared around the edge. You fall toward it. There is no wind, no heat, no sound, only the black circle growing until it fills your view. You cross the horizon, and you feel nothing change, no boundary, no jolt, only the stars behind you crowding together and brightening as their light is bent. You try to turn back. You fire everything you have in the direction you came from, and you discover that the direction you came from is no longer there. Every way you turn, every path you try, leads deeper in. There is no maneuver, no angle, no escape, because out has stopped being a place. And above you, in your final moments, the entire outside universe is compressed into a shrinking, brightening window, its light blue shifted and racing, as though you could watch the whole future of everything you left behind flash past in the time it takes to fall. And then the center, which is not a place but a moment, arrives, as certain as tomorrow. Now here is the detail that makes it almost unbearable to think about from the other side. Suppose someone you loved watched you fall in from a safe distance outside. They would not see you cross the horizon and vanish. Because of the way the black hole warps time, they would see you fall slower and slower as you approach the boundary. Your image would redden and dim, your motion would seem to freeze, and you would appear to hang there, at the very edge, growing fainter and slower forever, never quite crossing, an after-image stretched across an eternity that from your own point of view lasted only seconds. From the outside you never quite arrive. From the inside you fell straight through. Both are true. Time itself has come apart between the two of you, so completely that you cannot even agree on whether the fall has finished. There is no other place in the universe where reality splits like that, where two honest observers cannot agree on whether something has happened yet. And this, finally, is why a black hole's interior tops this list, above the iron rain and the glass storms, above the frozen nebula and the graveyard worlds, above the waiting supernova and the feeding black hole and the great fall of the galaxy and the blazing danger of the core. Every one of those places, as terrible as it is still a place. Each one still sits inside the ordinary universe, with a somewhere else beside it, a direction called away, an escape you could imagine taking even if you could never quite manage it. The hottest world still has cold space around it. The most crowded core still has the empty suburbs beyond. The Great Fall still leaves you free to move within it. In every single case, leaving remained one of the things that existed, even if only in principle. Inside a black hole, leaving is not difficult. It is not merely impossible in the way that outrunning light is impossible. It has been removed from the list of things that are real. The interior of a black hole is the one location in all of existence where there is no elsewhere, where away is not a hard direction but a deleted one, where the exit is not locked but has ceased to be part of the universe at all. There is one more layer to the terror of the interior, and it is the one that has kept physicists arguing for half a century, because it sits right at the boundary of what anyone actually understands. The singularity at the centre, the point where the mathematics predicts infinite density, is almost certainly not the real final answer. It is a signal that our best theory of gravity, Einstein's general relativity, has been pushed past its limits and has broken down. To describe what truly happens at the heart of a black hole, we would need a more fundamental theory that unites gravity with the quantum rules that govern the smaller scales, a theory of quantum gravity that we do not yet possess. So the very centre of the most terrifying place in the universe is also a blank spot on our map of reality, a place our physics can point to but cannot enter, an admission written into the equations themselves that here our understanding ends. Even the fate of everything that falls in remains a genuine puzzle. The physicist Stephen Hawking showed that black holes are not entirely permanently black, that they slowly leak a faint radiation, and over unimaginable spans of time may eventually evaporate away completely. But if a black hole can vanish, what becomes of everything that fell into it, every star, every world, every scrap of information about what went in? Whether that information is destroyed, or somehow preserved, or subtly encoded in the escaping radiation, is a question physicists are still wrestling with today. So the interior does not only take away the direction called away, it takes away our certainty about what is real, about whether the things that fall in are gone for good or merely hidden, and it does so at the exact place where the universe stops letting our theories follow. It is the most terrifying place not only because there is no elsewhere, but because it is the one place the universe refuses to explain. I want to sit with that for a moment, quietly, because it is the true bottom of everything we have visited tonight, and it says something about what fear even is. Think about every frightening thing you have ever survived in your life. Every one of them, you survived in part because leaving was possible. You could walk away, close a door, put distance between yourself and the danger, or at the very least imagine a version of events in which you did. The ability to leave, the simple existence of a direction called away, is so woven into everything we are that we never once think about it. It is the most basic assumption a living thing makes. Wherever I am, there is a somewhere else, and a black hole's interior is the single place in the universe that quietly takes that assumption away. It is not the heat, in the end, that makes it the most terrifying place. It is not the cold, or the radiation, or the violence. It is the absence of a way. That, more than any temperature, is what the word terrifying was always pointing at. And now, having fallen all the way to the bottom, let us climb back out into the ordinary night, because there is something waiting for you here that I think you have earned. Come back up, past the galactic core, past the great falling current of the galaxy, past the feeding black hole and the Death Star pinwheel and the waiting supernova, past the graveyard worlds and the frozen nebula and the storms of glass and iron, all the way back to here, to your room, to the quiet, to the ordinary dark outside your window, where a handful of faint stars hang in a calm and unremarkable sky. Everywhere we went tonight is real. Every one of those places exists right now, out there, under the same stars you can see. But look how far away they all are. 600 light-years to the iron rain, thousands to the graveyard and the dying star, 26,000 to the blazing core. All of that hostility, all of that violence, held at an immense and gentle distance, while you lie here, safe, in the rarest kind of place there is. Because that was the quiet truth underneath the whole journey. The calm sky over your head is not the universe's ordinary face. It is a local exception, a small and improbable pocket of peace in a cosmos that runs, almost everywhere else, toward the extreme and the lethal. We did not begin the night knowing that. We began by treating the dark sky as simple scenery, an empty and finished backdrop. But now you have seen what it is holding back, and how far away it holds it, and I hope the ordinary quiet feels different now. Not more fragile, more precious. The stillness you're lying in, the stable ground, the gentle dark, the fact that away is always a direction you can take, these are not nothing. They are the rarest and kindest things the universe knows how to make, and you were given all of them, for free, simply by being born where you were born. So let the far places stay far. Let the iron fall on its distant world, and the glass storm its blue sky, and the nebula freeze, and the galaxy fall, and the black holes keep their silent sealed interiors, all of it out there, all of it real, all of it a comfortable eternity away. And let yourself rest here, in the exception, in the quiet corner that the frightening universe forgot to ruin. The sky over you is calm tonight. That calm is rarer than you knew, and there is nowhere in all the terrifying places we have visited that would not trade everything to be as safe, and as still, and as gently ordinary as the little pocket of the cosmos you're lying in right now.